In this video, I'll go through the process of converting a Fischer projection model to a Haworth structure. In other words, I'll detail step by step how to go from the line structure of a carbohydrate to the ring structure. To detail the process, I'll use D-glucose to convert to the ring structure. The structure shown on this slide represents the Fischer projection model of D-glucose. I'd recommend that you start by numbering the molecule. Recall that glucose is an aldohexose, meaning it has an aldehyde functional group at carbon 1 and a total of 6 carbon atoms. Instead of showing the condensed formula for the aldehyde as CHO, I went ahead and I'm showing the expanded or the structural formula so that you can see the actual bonds that are present in that functional group. In addition to that, all the other carbon atoms are numbered so that we can keep track of the carbons as we go through the process. In order to go from the line to the ring structure, a hemiacetal must form. Hemiacetals are formed as a result of a chemical reaction between an alcohol functional group and an aldehyde functional group. Notice in glucose there are several different alcohol functional groups that are present, and there's one aldehyde functional group. So you have several options as to how this hemiacetal can form. But the way that it will form will depend on the lowest energy or most stable compound that could be created. Because this reaction is an intermolecular reaction, meaning that both the alcohol and aldehyde functional groups are within the same molecule, it's going to cause a ring to form. And so in order to determine how the ring forms, it'll go back to which ring is going to be more stable. Although rings can contain a minimum of 3 atoms, the stability or the energy associated with those rings varies. The most stable ring, lowest energy ring, is a ring that has 6 atoms. The next most stable would be a ring that has 5 atoms. So if a ring can form with a total of 6 atoms, this is the option that will likely occur, specifically for these hexoses. So in the case of glucose and any of these other aldohexoses that we discussed, carbon 5, which is your chiral carbon that is farthest away, the alcohol functional group attached to it is the carbon, or the alcohol that reacts to form the hemiacetal. Recall this is also the hydroxyl or the OH or alcohol functional group that determines whether or not it is a D or an L sugar. So that same alcohol functional group is what reacts to form your hemiacetal. So the reaction arrow that you see here, or the arrow that you see here, is showing how the electrons are moving from the oxygen that is attached to carbon 5 to carbon 1 of your aldehyde functional group. Now when doing this, this oxygen is now sharing electrons with that carbon. Remember, anytime atoms share electrons, they form covalent bonds. This oxygen shares the electrons with the carbon of the aldehyde functional group because it is the most reactive position in this molecule. This position is also referred to as the anomeric carbon atom. The anomeric carbon is simply the carbon that was originally the carbon of a carbonyl, so a carbon-oxygen double bond. So carbon 1 of the aldose is your anomeric carbon, and carbon 5, which is your chiral carbon that is farthest away, that oxygen shares its electrons with that carbon to form a bond. Please note that this is not a complete structure and it is not a correct structure. I am simply showing the stepwise process as to what took place. And so right here, this is showing what happened after the oxygen that was attached to carbon 5 shared its electrons with the anomeric carbon, so carbon 1. And so when those two atoms shared those 2 electrons, a bond formed between them. So the bond is highlighted in red to show how that oxygen and carbon 1 shared electrons. But if you notice, carbon 1 now has 5 bonds. Carbon can never have 5 covalent bonds. And so you've often heard that when chemical reactions take place, Oftentimes, when new bonds form, old bonds have to break. So when that new bond formed between the oxygen and carbon 1, it's going to cause old bonds to break. How can you determine the bonds that will break? Think back to how covalent bonds form and how atoms prefer to form covalent bonds and the number of bonds they prefer to form. Thinking back to the Lewis dot symbol and the Lewis electron dot symbol for oxygen and carbon. Oxygen belongs in group 6A. It has 6 valence electrons. If you do the electron dot symbol for oxygen, you'll have 4 electrons that are paired up, 2 electrons that are unpaired. Recall the number of unpaired electrons corresponds with how many bonds an atom wants to form. Since oxygen would have 2 unpaired electrons, in its most stable form, it would form 2 bonds. However, this oxygen right now has 3 bonds, so it's not in its most stable form. Do the same thing with carbon. Carbon belongs in group 4A, so it has 4 valence electrons. Placing 1 dot on each side, you have 4 unpaired electrons. Carbon in its most stable form is going to have 4 bonds around it. Right now, this oxygen has 5 bonds. So you have 2 atoms that have electrons being shared that does not result in the most stable form. So when that new bond formed between the oxygen and carbon 1, it would then cause old bonds to break. To determine which bonds break, think back to which ones are the most polar, the more reactive, because those electrons are not evenly spread out. The oxygen-hydrogen versus oxygen-carbon. Oxygen-hydrogen bonds are more polar because oxygen is a highly polar or has a very high electronegative value, whereas hydrogen does not. So the electronegativity differences between oxygen and hydrogen is greater than that of carbon and oxygen. So the oxygen-hydrogen bond is going to be more reactive because of the uneven distribution of the electrons. As far as carbon 1, you have 2 carbon-oxygen bonds. But what happened was when that new carbon-oxygen single bond formed, it would cause one of the bonds in that double bond to break. So when that oxygen-hydrogen bond broke and one of the bonds in that double bond broke, you can simply imagine that the hydrogen that was initially bonded to the oxygen that made the ring was simply transferred to the oxygen where the double bond was originally located. This is how you end up with an OH group or an alcohol functional group on carbon 1, which is your anomeric carbon. So here, if you notice, for carbons 2, 3, 4, and 5, the bonds are vertical. But for carbon 1, I just drew them off to the side. The reason why is because that OH group that formed could be pointed up or it could be pointed down. The difference between the two will determine which type of glucose or which type of monosaccharide you have present. The 2 types of monosaccharides that can form during the ring formation are called anomers. And the 2 types of anomers are alpha and beta. Alpha anomers and beta anomers are determined by looking at the relationship and the direction of the hydroxyl, so that OH group or that alcohol functional group that is attached to your anomeric carbon, which is carbon 1. So looking at the relationship between it and carbon 6. Alpha anomers have an alcohol functional group on the anomeric carbon that is trans to carbon 6. Carbon 6 will always stick up out of the ring for D sugars. And so remember, trans means that they're on opposite sides. So since carbon 6 is sticking up, in an alpha anomer, that hydroxyl on the anomeric carbon has to point down, as shown in red on this slide. For the beta anomers have hydroxyl groups on the anomeric carbon that are cis to carbon 6. Cis means same side. So again, carbon 6 points up in the D sugars, So therefore, the hydroxyl on the anomeric carbon of a beta anomer would also point up. So knowing whether or not you need an alpha or beta anomer tells you how to direct the hydroxyl on carbon number 1. For the other carbons, you have to do a little more digging. For the remaining carbons, carbons 2, 3, and 4, you want to refer back to the Fischer projection or your line structure. The Fischer projection or line structure, whatever you want to call it, when looking at it for carbons 2, 3, and 4, the mnemonic left up to you may help you. Left up to you simply means that everything that is on the left points up. Therefore, everything that is on the right will point down. So looking at carbon 2, the hydrogen is to the left, the hydroxyl is to the right. So for carbon 2 in the ring form, the hydrogen is going to point up because it was left up to you, meaning that the hydroxyl will point down. The same thing for carbon 3. The OH was to the left, so it points up. The hydrogen was to the right, so it points down. And carbon 4. The hydrogen was to the left, so it points up. The hydroxyl was to the right, so it points down. Carbon 5, we've already dealt with carbon 5 because that hydroxyl was used to form the ring. Carbon 6 is always going to stick out of the ring. This is an achiral carbon. It doesn't participate in the ring formation. It always sticks up out of the ring for these D sugars. And so here, shown on the right, you have the structure of alpha D glucose. But what if you were wanting to draw the structure of beta D glucose? To draw beta D glucose, the only difference is how the hydroxyl is arranged around the anomeric carbon. Anytime you're dealing with D-glucose, you have to make sure that you're using the line structure of D-glucose, which is always the same. So for carbons 2, 3, and 4, again, it was left up to you. That didn't change. So for carbon 2 and carbon 4, the hydrogen atoms are both pointing up still. The hydroxyls are both pointing down still. For carbon 3, the hydroxyl is still pointing up. The hydrogen still points down. Again, none of those change. We've already dealt with carbon 5. Carbon 6 is still sticking up out of the ring because it's a D sugar. So the only difference now is how the OH was arranged around the anomeric carbon. So again, now you have the structure of beta D-glucose. So when you compare those structures of alpha D-glucose and beta D-glucose, the only thing that is different is the arrangement of the hydroxyl around the anomeric carbon. Now on this slide, I took out the hydrogen atoms because recall in a skeletal structure, you don't always see those carbon-hydrogen bonds. So you may see the structures drawn with the carbon-hydrogen, you may see them drawn without. But regardless, if you see a hydroxyl group that is pointing up, you know that the hydrogen has to point down. Or if you see the hydroxyl group pointing down, the hydrogen has to point up. So again, comparing these two structures, the only thing that is different is the arrangement around carbon number 1. So looking at carbons 2, 3, and 4, those are used to determine the identity of the monosaccharide. Looking at carbon 1, that determines the anomer, so whether it's alpha or beta. This same process can be used regardless of what aldohexose you are working with. Simply determine whether it's alpha or beta. Place that OH either up or down on the anomeric carbon. Up for beta, down for alpha. This is assuming that we are dealing with a D sugar which has carbon 6 up. More specifically, we can say cis for beta, trans for alpha. For carbons 2, 3, and 4, refer back to your line structure or your Fischer projection. Everything that was to the left is going to point up. Everything that was to the right would point down. Carbon 6 is up in the ring, or outside the ring, I should say, for the D sugars. But if we were dealing with an L sugar, carbon 6 would be pointing down. But we're going to be dealing with D sugars in this course, so you'll always have the basic structure where you have a 6-membered ring known as a pyranose that contains carbons 1, 2, 3, 4, and 5 inside the ring, in addition to an oxygen, and carbon 6 sticks out of the ring. So hopefully this will clarify how to convert your line structure to a ring structure. The more practice that you do with this, you'll see that it becomes somewhat redundant and pretty much the same over and over and over. For the most part, once you know you're dealing with an aldohexose, go ahead and draw that pyranose ring where you have your 5 carbon atoms and oxygen in the ring, carbon 6 up out of the ring. Then, depending on if it's alpha or beta, arrange the OH on your anomeric carbon, which is carbon 1. Then refer back to your Lewis structure, which is your line structure, to determine the arrangement around carbons 2, 3, and 4. So again, hopefully this helps you. If not, feel free to let me know.